All right, welcome. So we have the recording started. I have our home screen up here for our multimeter class. I just activated the week 4 information, and tonight we're actually going to go through a PowerPoint presentation that I put together and do some live multimeter stuff with my document camera that we've set up here. So we have lots of stuff to do. The PowerPoint we're going to be finishing tonight is actually the one back from week 2, but we'll get that thing knocked out, and of course we'll end tonight on a tech tip as I go to use the multimeters in class. In fact, one of the meters I just opened it up. It's this one right here. It's one of those ones you get from Harbor Freight. I want to say they cost less than I don't know, $6, maybe $7, or sometimes if you buy a bunch of junk and you got a coupon, you can get them for free. Anyways, I just took that thing out of the box here a minute ago. We're going to be playing around with that guy tonight, and I'll show you some different tech tips on those basic multimeters. Because remember, our goal is to give you the most testing capability with whatever meter that you have. So with that, what we're going to do is we're going to go into the modules real quick. Remember that we're still tonight, we're finishing this basic electricity presentation part 2. We're going to finish that up tonight as we mix in some stuff about using multimeters and some of this week 3 information. I have all kinds of great documents and links that will take you through using a multimeter, whatever multimeter that is that you have. And essentially your assignment for this week, if you will, was to try to score yourself an electrical multimeter that you can test some stuff out with. All right, and it looks like my internet's being a little slow. It's still thinking about loading that thing. I'm gonna go back to modules and switch a few things around so that we can open up that PowerPoint presentation. So we will switch over to the PowerPoint. Very good. And kind of get back to where we were. We'll go right here. All right. It's great to see you guys here tonight. You know, when you see these diagrams, it can get a little tricky. And I mentioned before that, you know, there's series circuits like these ones where there's only one path for current to flow. And then there's parallel circuits, and we talked about that. And I also said that I'm not going to make you in this class do a bunch of the math to calculate the circuits. But the reason that we do the math is really just to understand the relationship. So what I'll do is I'll just do, you know, 1 or 2 of each one on my slides here. I'm going to get my annotation tools up here. Get some colors going. All right. So let's start with this one right here. We're going to go through this circuit right here. And there were some laws when it came to series circuits. Remember that there's only one path for the current to flow through. So however many amps is leaving the battery from the positive post and flowing through the circuit, that same number of amps needs to be entering the other side of the battery, right? And so because of that, one of the major rules with series circuits is that the current flow is the same throughout the whole circuit. The voltage has to then be shared along the circuit. So what that means is that each one of these resistors, I got this guy right here. I'm going to go ahead and type something. I'm going to say this is going to be resistor 1. Oops, not 21, resistor 1. This guy's going to be resistor 2. And this guy's going to be resistor 3. Well, each one of those resistors would use up a little bit of that voltage. You can't have any voltage left over at the end. So each one of those guys is going to have a voltage drop. Last week, we also, and the week before, for that matter, we also talked about Ohm's law, and I drew this little pie chart looking thing. Boy, that's an ugly circle, but you get the idea, where we said, hey, we got volts, amps, and ohms, and if I want to figure one out, all I got to do is cover them up. So for instance, if I want to figure out, well, let's start with this. If I want to figure out my total resistance here, how I would do this is I would assume that the wiring are okay. Whenever you're doing these math problems, you can't assume that you can't figure, oh, the wires are going to have resistance. So what you do is you figure that the wires have no resistance in them. So how much resistance do I have? Well, I have 4 ohms at resistor 1, 2 ohms at resistor 2, and 6 ohms at resistor 3. How do I figure out what my total resistance is? I just add those suckers together, right? So 4 and 2 and 4, that's 6, plus another 6 ohms. Oh, that's going to give me a total of 12 ohms of resistance. So that's my total resistance. So I know what my resistance is right here. I know that my resistance is, I'll change my colors on this. So I have 12 ohms. I also know it's a 12-volt battery. So I'm going to write 12 right there. And if I want to figure out the amps, oh, well, that's just 12 volts divided by the 12 ohms. And guess what? 12 divided by 12, that's going to equal 1 amp, or 1. So I have 1 amp of current leaving the battery. And that means I also have 1 amp of current going back into the battery on the other side as that battery discharges. That also means that I have 1 amp of current going through resistor 1, resistor 2, and resistor 3, right? So how many amps? I have 1 amp. Now, I can figure out then, because I have all this information, I'm going to go ahead and start clearing some of my scribbles here. I could then figure out how many, let's see, 1 amp. I can figure out how many volts each one of these guys uses up. How do I do that? Well, I'll change my color. The volts, if this is what I want, okay, well, that's just the amps multiplied by the ohms. Those two guys are together. So if I were to cover that up with my finger, I would say, hey, okay, I want volts. That's amps times my ohms. And I can figure that out. So all I have to do, I have 1 amp flowing. So 1 amp times 4. Oh, this is going to have a voltage drop. And I'll change this color here. This is going to have a voltage drop, or VD, of 4 volts. This guy right here, he's going to have a VD of 2 volts. And this guy over here is going to have a VD voltage drop of 6 volts. All right. How are we doing? Questions on any of that stuff? Okay, well, so in an electrical circuit, remember, we don't want to have voltage drops on the wires and stuff. We don't want to have any voltage drop in these wires. We want to drop the voltage on our components that we're trying to operate, which in this case would be our resistors. So we expect to have the voltage drop there. So if I add these up, again, 4, 2, plus 6, that's going to equal up to our source voltage, which is 12 volts, and everything works out in this circuit. And honestly, I find that most people, they don't have too much problems with series circuits. Series circuits are pretty simple for the most part. They make sense, and you know, it's not too far out of the box. Most folks get series circuits okay. It's when we move away from series circuits that kind of it gets a little crazy on us, and it can become kind of a head scratcher to figure out what's going on. So if I go back to my presentations here, remember that rules for series circuits, the total voltage drop had to equal source voltage, right? The higher the resistance, Ohm's law says the higher the voltage drop will be on that particular component, and the current flow is going to be the same. If I go back here, the current flow is going to be the same through the entire circuit. So those are the big rules there when it comes to series circuits. When we move down to parallel circuits, stuff gets a little weird, because now I have a separate path for current to flow. And probably the thing that messes people up the most, I mean, I think most people get that, hey, each device receives full source voltage because I have 12 volts going to this guy, I got 12 volts going to resistor 2 there. Okay, that makes sense. But what goofs everybody up is this right here. The total circuit is less than the less resistive branch. And a good way to think about it, is if you had lanes on the freeway, if you will, and let me pick a different color here. And let's say this lane here was really backed up. There was lots of traffic. So the cars weren't moving real fast, but they're still moving slowly a little bit. That lane has a lot of resistance, if you will. If the other lane was moving real good and only had a few cars they were zipping by, well, still overall on the road, you'd still be moving more cars down the road with 2 lanes than you would with just having the one fast lane, right? So the total resistance is always going to be less than the lowest branch, because there's more than one path for the current to flow. You know where people get into trouble doing like wiring and stuff on their car is they start making their own parallel circuits oftentimes, and they don't realize it. If I'm going to take this circuit that we have, I'm going to modify it a little bit. I'm going to put a fuse right here. Let's say there's my fuse. I haven't drawn it all that good, but that fuse happens to be a 10 amp fuse. Okay, and I will go back and get my drawing tool out. Gonna highlight this thing. So there's my fuse. That's my circuit protection device. It's rated at 10 amps, and it happens to run a couple of circuits. Maybe maybe here we have this R1. Let's say this is our, well, I don't know if that'll come up being, I'll make it orange. This is our dome light. Okay, now this other circuit, this was our car stereo or our radio system, okay? And the engineers from whatever car company we're saying we have here, a Honda, Ford, Toyota, whatever, they engineered, hey, those 2 circuits, if they're both running, they shouldn't take more than 10 amps. But I come through here and I upgrade the stereo, and then I decide, well, you know, that upgraded stereo still isn't enough. And now I'm putting this amplifier in here. So I'm going to put an amp on here, and he's going to ground. And then You know, maybe I add in some extra like charge ports so I can be charging 25 cell phones at once and my MP3 player or whatever. So I'm going to put, I'm going to say that this guy here, this is a charge port. Okay. So what I've done without realizing it is now I've added a couple of parallel circuits. So I still have current flowing through the original two, right? That wouldn't normally take more than 2 amps. But now I have some current flowing through this charge port. Okay. But then I have probably a lot of current trying to go through my new car stereo amplifier. And so what's happened is that every time I add a branch, more current can now flow down these branches. Why? Because total circuit resistance is going to be less than the lowest resistive branch. And so now I could get to a spot where I'm blowing fuses right and left because I've made these extra parallel branches. Remember that Ohm's law tells us, it says, hey, if I have the same amount of voltage from the battery, but the resistance gets to be lower, right? Less than the lowest resistive branch, that means the current flow is gonna go higher. And it makes sense if you think about it, hey, there's just more ways for the current to flow. So you see this all the time on vehicles, especially when people have added their own extra accessories and they keep back tapping the same fuse, and then they have all kinds of problems. And then you'll see people, they'll go, you know what? I'm having all kinds of problems with that. I'm going to get rid of that 10 amp fuse. There must be a problem with that fuse. And then they put in, you know, a 20 amp fuse or a 30 amp fuse. And now the wiring here on this side of the fuse ends up getting burned up because it's trying to flow more amps than the engineers planned for. So anyways, a lot of times we make parallel circuits and we don't realize it. And that can lead us into problems. A common place you could make a parallel circuit, if I scroll down on this presentation here, let's see if I can get it to come to life. Let's skip forward a little bit. Is imagine for a minute that I was going to test this circuit. Well, if I take my meter, I'm going to draw just a red box for my multimeter, and I have one lead is going to go right here. And let's say the other lead, the negative lead, I have it go down to the negative battery post. Technically, what I have done here with my meter is my meter is now a parallel branch, isn't it? Because now current could flow through the meter to ground. So since this is a meter class, this is pretty important for us to understand, is that you'll be looking up specifications on multimeters. And one of the things you'll hear is that, oh, you want a meter with a minimum internal resistance of 10 mega, or think a million ohms. Okay, why do we want that? Well, basically what I want to have is I change the color again, is I want to have a really, really big resistor that has a lot of resistance so that very little current can actually flow through the meter because its internal resistance is so darn high. Okay, we're going to measure that out here in just a minute. So one thing that meters should have is a very high amount of internal resistance when they're set to volts. All right, if I let me clear some of these drawings. Clear my drawings, and we'll keep moving. So we beat you up with parallel circuits, but I didn't make you do the math on those. But I'll go ahead and do this one together just to kind of show you how it would work. And the method that I like sounds kind of silly, but I liked what I ended up calling total current method. I wouldn't say that's like an official name. That's just kind of what old Mr. French started calling it years and years ago. And what that means is I found the easiest way. If I remember when I was in school, in electronics school, like my teachers would give me just pages and pages of this type of math problem to figure out. You know, and so it was like, well, let me figure out the easiest way to do this. And then I had to figure out, well, what's an easy way to teach this to other people when I first started teaching, and it was a challenge. I was doing electrical work every day in the shop, and I was kind of like the electrical go-to guy in the shop. But then to teach what I knew to somebody else required a whole new set of skills, and so that's when I really developed this total current method. So it's not just the way that's easy to calculate, but it's a way to kind of make sense of stuff. Remember that if however many amps I have flowing out of the battery, I got to have the same amount of amps flowing into the battery, right? That's one of Kirchhoff's laws. And I also remember that, hey, we got that Ohm's guy, and he had his law, right? That basically said, hey, if I know two of these guys, I can figure out the third. So if I know the volts and the ohms, I can calculate the amps, or if I know the volts and the amps, I can calculate the ohms, and vice versa. So what I can do here is I can figure out this total current. Now, remember, it says IT. That's old carryover. Current used to be called intensity. So I'm going to type over that. Instead of it being IT, I'm going to say it's, I was going to write TA, but I probably shouldn't write that. I'm going to say it's amps total. So I don't want you confusing it with anything else. All right, so amps total. So how do I figure out my amps total? Well, if I were to calculate how many amps were flowing, let me try this again. If I were to calculate how many amps were flowing, oh, no, I'm on an arrow. How did I do that? Through this resistor 1, and then I calculated how many amps were flowing through resistor 2, and then I calculated, in this case, because there's 3 of them, how many amps were flowing through resistor 3. All I'd have to do is add up those 3 current flows, and I would know, well, that many amps must be leaving the battery, and that many amps is going into the battery, the sum of those 3. So that would be my total current flow, or total amps. And I can do Ohm's law to figure that out pretty easily. I am going to look at some information here. It says right here that this is a 12-volt battery. Okay, so 4 ohms. So if I have a 12-volt battery, I'm going to divide it by 4 ohms for that first one. 12 divided by 4 is 3. So what that tells me is that, I change this. This guy has 3 amps going through him. And this one, okay, that's going to be 6. So 12 divided by 6. That's pretty easy math, right? So that's going to tell me that I have 2 amps going through that guy. And then if I have resistor 3, well, he's 8 ohms, right? So that one's a little bit different. That's going to give us kind of a weird number. So I'll tell you what we'll do here. We'll cheat a little bit. If I can switch this over. Okay, and I'll change my share to the screen. Boom, there we go. And I'll minimize that for a second. We'll throw up that calculator and we'll say, all right, I have 12. I'm going to divide that by 8. And that's going to give us 1.5. All right. So now that done that, let's see if I can go back into presentation mode. Annotate. So text, we had figured this out. So this is 1.5. This number 2, 12 divided by 6 is 2 amps. And then this one was going to be 3 amps. I unfortunately erased all my drawings when I closed it out, but all I have to do is add those 3 guys together. So 3 plus 2 is 5, and then we got another amp and a half, so we got 6.5. All right, so what I have here, total current flow on this guy is 6.5 amps. Now, if I want to figure out the total resistance, all I have to do is Ohm's law again. So let me get my drawing tool up, guys. So I have 12 volts, all right, volts, amps, and ohms. I know the amps is 6.5 now, so I'll go ahead and type that over here, 6.5. And I'm going to divide those 2 guys out. What you'll notice is, remember, one of the rules is that the total circuit resistance has to be less than the lowest resistive branch. The lowest resistive branch is 4. So I know whatever crazy number I get, it has to be less than 4. If it's 4 or more, I did my math wrong. Okay, so let's switch. Get this out of here, and I will throw up the calculator again, because now what I'm going to do is I'm going to say I got 12 volts. I'm dividing it by 1. Oops, I'm dividing it by 6.5 amps, and I end up with 1.85. So my total resistance here is 1.85 ohms. Now, is that less than 4? Yes, it is. So that's my first indication that, yeah, that works. And I could kind of go backwards on this thing if I wanted to check my work. For that matter, let's see. I'm sharing the whole screen. Okay, I just wanted to make sure that everybody can see what I'm doing here. So I calculated my total resistance is 1.85 ohms. What I could do is work backwards in that if I took 1.85, I divided by 12 volts by 1.85, it would give me the 6.5 amps, and I could end up getting back to these numbers. So it's just, the math is a way to prove the concepts and the theory as to what's going on. I find that for some students, doing the calculations is helpful. For other students, maybe not so much. Most of you auto students, you tend to learn more from actually, getting out there and testing stuff, actually doing stuff. And I totally get that. But I kind of felt like I wouldn't be doing you a good service if I didn't show you all the different ways that you could calculate some of these some of these questions and problems and different things. All right. So, all right, I'm doing a little bit of housekeeping stuff, just moving stuff over. All right. So we beat you up with parallel circuits. We kind of ground into the series circuits. Remember that a series parallel circuit is just a combination of the two. It's nothing crazy outside the box. What do you do if you were faced with one of these circuits and you had to do all the math calculations and stuff on there? You would figure out the parallel part first, and then from there you just treat it as a series circuit. And so I guess a way to look at that is, hey, if you have a series parallel circuit, well, half of that circuit's going to act just like a series circuit would, and the other half's going to act just like a parallel circuit would. And so as long as you remember those rules, stuff will still continue to make sense for you. For instance, like with this one that's on the screen, if this resistor right here were to burn up and fail, guess what? Neither one of these guys would work, because the series part is what failed, what failed in service, and that would kill the current flow to the other two guys. However, if just this one failed, then this guy would still work, and so would the other branch, right? These two would keep working because it failed in the parallel half. Remember, the parallel part's going to apply to all the rules of parallel circuits, and the series half is going to apply to all the rules of series circuits. All right, so let's actually get to doing some circuit problems on these guys. We'll get away from the math for a bit. Remember, I said there's two flavors, opens and shorts, and kind of variations of that theme, okay? Now, what is an open circuit? Well, I'm gonna say this chocolate one over here, this is my open circuit. O-P-E-N. What is an open circuit? I'm just going to say CKT for circuit, is essentially really high resistance. Okay. Well, what's a short circuit then? Well, a short circuit, he's essentially just too low of resistance. T-A-N-C-E. All right. So let me give you an example with the Ohm's law pie chart. We'll see how well we can draw it this time. I've already messed it up. All right, there we go. Okay, if my 12-volt battery stays the same, I'm just going to write 12 volts. Remember, if my resistance goes really high, Ohm's law told us, hey, if your resistance is high, hey, the current flow is going to be too low. Well, let's say the resistance is high because the circuit's open. The switch is open, the wire's disconnected. That's essentially infinite resistance. Guess what? I'm not going to get any current flow. Okay, the circuit's open, there's no current flowing, everything shuts off. All right, well, what about the opposite of that? Is if the resistance is too low, well, now I'm going to get too much current flow. And I might get current flowing into other circuits I don't want it to flow in. Where it gets tricky is on a car. If you have too much current flow, there's usually going to be some type of protection device like a fuse, sometimes a circuit breaker, and that fuse is going to pop. And so then after the fuse blows, it becomes an open, right? but really it's a short. You keep putting fuses in, it keeps blowing them, and it becomes an open when the fuse blows. So those are your circuit problems, shorts and opens. Let's see how we would diagnose those. So we have here an interruption in the path for current to flow. That's an open, right? How can we find it? We could find it with our meter, right, which could be called a DMM for digital multimeter. The old term was DVOM for digital volt ohm meter. You could maybe use a test light or something like that. How would we find this though? Well, I'm going to draw that meter box again. Here he is. And I'm going to set him on volts. And I would take one lead, and I would take my positive lead, and I would go right here to the battery terminal. I'm going to take the negative lead. I'm going to go over here to ground. And I just start probing this thing at different spots. So right here, he would read 12 volts, let's say. This is a 12-volt battery. But then if I move the lead over here, oh, he's also going to say 12 volts. But now, if I moved him right in front of the light bulb, guess what? If the wire really is broken right there, when I move it down here, well, now that guy's going to say 0 volts. And essentially what I've done is I've kind of broken the car down into sections. At some point in a car, just nature of the beast, because there's split loom tubing and all that stuff, like at some point you got to go digging and physically find where the open's at. But what you're trying to do is, remember we talked in our class that there's 5 miles of wire underneath the average car. You're trying to break down that 5 miles of wire into the smallest area possible, right? So by using my voltmeter, I can kind of divvy things up and break it down into segments and start testing out where we want. And so I ultimately don't have to dig through as much wires on the car. So that's how you would diagnose an open circuit. It seems really easy on a computer screen here when we're talking about it. You put this in the confines of a car, everything does seem to get a lot more complicated. But this is how you do it. Okay, so let's clear that out of there and we'll keep going. So here, remember an open circuit, incomplete path for current to flow. What have they done right here? Well, here's our open, right? We've highlighted it there. In the real world, you wouldn't know that that connector is open. So you start testing stuff around, and you put your voltmeter here and you put it right behind the light switch, and it says 12.6 volts. And then where's the next easy spot to get? Well, I can plug it in right before the lamp. And of course the lamp's not illuminated. That's my problem. So I plug it in before the lamp. And now I have 0 volts. So I know that somewhere between the light switch here and the lamp there, I have it open. Now, I have another rule for circuit problems. And this isn't like a Kirchhoff rule or an Ohm's law. This is just the Mr. French crazy rule, okay? This is what I've found from experience is that, circuit problems are C and C. C. What's C and C? The first C is components. The second C is connections. And what I should add up here at the top, I'll make this red here, is that most. So is this saying all circuit problems? Well, heck no, okay? Most of the time, though, when you're in a normal situation and not in, you know, a crazy deal where you have a car that got driven into a lake or something weird like that, most of your circuit problems that you will encounter are CNC. They're either bad components, right? Whether it's a defective switch or a burned out lamp bulb, or they're bad connections, high resistance connections. So where do I like to test stuff? I like to test stuff at components and at connections. Plus it gives you a good point to test stuff. What I don't want to do is I don't want to see you stripping the insulation off the wires or poking. I've seen guys try to poke their meter probes through wires, and they end up making more problems in the car than they started off with. They end up making more issues there, and they make a bunch of bad connections because they're probing around on stuff. You can get a good connection point at a component or where two wire harnesses come together, right? So components and connections are where most of your circuit problems usually are, and they usually lead to a high resistance problem. And so again, we can use our voltmeter and we can divvy that out and go from component. Here we went to the backs of two components, and then we ended up finding that our problem was in the connection point in the wiring harness between those two components. Okay. All right. And I'm gonna just gonna check the chat real quick, because I haven't done that. Just to make sure that, remember, if you have questions, you can obviously turn your microphone on and yell out your question. You could raise your hand. There's a little way to do that on the Zoom interface here, or you could always type it into the chat. All right. Now we'll keep moving forward here. So diagnosing a short circuit. This would be an example of a short circuit that would, you know, cause an issue there that might cause something to flow too much current, or cause something to be on when you didn't want it to be on, that type of thing. So how would I do that? We have shorts to power, shorts to ground. Here I have a short to power. Okay, remember we said that shorts are usually not enough resistance. We could have two feed wires here. Essentially, I have a voltage feed wires that are pinched together, causing a short. One thing about short circuits is that this is one where really being able to read the wiring diagram can help you out quite a bit. So I have wiring diagrams are a must. And let's work a couple examples. Now, this is the short to power. And so the short to power would be something, for example, I need to modify this diagram real quick. Okay, and I'll get to this question on the chat in just a second. I'm going to modify this diagram. I'm going to put an on-off switch, right? Let's see here. No, I need to put this. I need to put this on-off switch right here to work for my example. So here's my switch, and I know it's drawn really bad, but the switch is open. I'll type in here. I've turned the switch off. Okay, so I have the switch and it's off, but guess what? This short is here, and so power is coming through here, and it's grabbing over and it's going over there, and what would happen is that the light would be on all the time, even with the switch off, because I have a short here to power. So when I have a short to power, usually what helps the most is to start disconnecting things one at a time in a sequence, right? So if I had a short to power and I had some connectors in there, I'm going to draw a couple connectors. I'm going to put a connector there. I'll put one there. And I got the switch here that can be a disconnect point. Well, I got a connector there and there, let's say. What I could do is then I disconnect this one. Of course, the light goes out. The switch turns off, the light's still on. If I disconnected this point, the light would then turn out, right? And then, of course, this wouldn't do anything. If I disconnected the ground, that would turn the light off. And by doing so, ultimately, I could isolate that my short to power is somewhere right over here. And remember when I said before, at some point, you got to go digging? Well, you'd have to go digging to find where that short's at. Okay, so we have a question on the chat. It says 2012 Honda open key. I do not see the light on the dashboard, but the main 50 amp fuse is good and the key is on. So if you don't have lights on your dash, the fuse is good and the key's on. Really what you need to do is start testing for power. Like to me, if I don't have stuff turning on and the main fuses are good, the first thing I want to make sure is that, do I have source voltage, right? Like a lot of these tests, we're assuming that we do have 12 volts here in our battery, right? So make sure that your battery voltage is good and then start looking for opens. I could have a bad connection right at the battery. I could have a bad connection further down the food chain. And what I would want to do is I'd want to find the wiring diagram and start to backtrack at easy test points, components and connections that are easy to get to see where do I have power, and then oops, where do I don't have power? And right between where you have the power and you don't have the power, that's going to be where your problem lies. So Tom, that's a good question about your car. Hang on to that, and what we'll do is maybe we'll look at this particular car in a wiring diagram in just a minute, okay? And what I would like you to do, Tom, is give me some more information about your car on the chat and what exactly the complaint is, and if you tested the battery's voltage, and then what circuits on your car work and what circuits don't work. Okay. I have one more short I need to talk about, and that's a short to ground. And here's what's really important. My recommendation is don't do the smoke test. Now, I know some of you out there, you're wondering, well, what the heck's the smoke test? Remember that cars, if they've been well engineered, they will have, gosh, this is really looking bad. They'll have a fuse, right? I'm trying to draw the electrical schematic symbol for a fuse. They'll have a fuse in there. That fuse is there to protect the wiring. Well, if I have a short to ground, what that means is current flow is going to go from the positive battery here through the fuse, and it doesn't have to go through this load. It can just go boom, straight to ground, which is where it wants to go. And so Ohm's law tells us, hey, my resistance, it just went way down. So that means the current flow, the amps, that's going to go way up. And so what should that do? That should blow this fuse out. So typically when I have a short to ground, I'm going to end up with blown fuses. And I put a new fuse in there and it blows again. I put another one in there, it blows again. It gets pretty expensive to keep putting fuses in there. So the smoke test is people would they'd take a paper clip, or they'd take their pocket screwdriver. I've seen some guys put some tinfoil around a fuse. I had a customer, he had a bullet in his fuse panel. Anything to basically bypass this fuse and jump this gap, okay? Now, Notice I said smoke test. I actually worked with some mechanics, and it wasn't just one guy, one crazy guy. I worked with multiple guys. How did they figure out where they had a short to ground? And they literally would ram their screwdriver in there, or they put a jumper wire on there and bypass this fuse. When they bypassed the fuse, the circuit turned on, and guess what? A lot of amps started flowing through there. Well, so many amps would flow through there, pretty soon, guess what? It'd start smoking. It'd start burning up the wires. Where would it burn the wires up? It would usually burn the wires up near where they were actually pinched to ground. And so once the wire started to melt and they saw where the smoke was coming from, they would then take their screwdriver out of the fuse panel and, you know, dig around there and find where all the melted wires were. Sometimes though, most of the time, that would require them, they'd end up having to change the whole dang wire harness because so many wires got melted in that process. So you don't need to do the smoke test. I guess you can figure stuff out that way, but you can cause a lot of damage on the car and cause your customer a lot of extra work that they wouldn't need to really have to do. So don't do the smoke test. How would I figure this out? Well, if I didn't mind blowing a bunch of fuses, if I draw and I put my fuse back in here, here he is. If I put my fuse back in there, I could just, again, start disconnecting the circuit at different points, just like I did before, and isolating this thing. So I'll disconnect this light bulb. Oh, the fuse still blew. I'll disconnect that resistor. The fuse still blows. I'll disconnect, maybe there's a connection point right here, and I disconnect it there. Fuse still blows. There's a connection point here. I'll disconnect it there. Oh, the fuse doesn't blow. And so now I know that my short to ground is somewhere right in here. So I can isolate it that way and do a lot less digging, okay? So that's how you would figure out that type of problem. Now, we tend to get really focused in on shorts. In fact, I've had people say, oh, I got a dead short, you know, and usually they don't understand what the heck they're talking about. They have an open circuit and they call it a dead short. Remember, shorts are low resistance, opens are high resistance. If you had a dead short, maybe you had a short circuit, now it blew the fuse so the circuit's dead. But it's kind of a misnomer. If you have a short circuit, the current flow is going to go high. In an automotive circuit, that should blow a protection device, a fuse. So that is how you would figure that out. Again, this stuff seems easy until you until you get it on a car and really have to start digging around. In this picture, what you find here is that our courtesy lights would be on all the time, even though the door switch is open. Like I've closed the door, so the door switch is open. The courtesy light shouldn't be on, but if there's a short there, the light stays on all the time. It runs the battery dead overnight. That's kind of a common one for a parasitic draw. So, all right. So test equipment, wrapping this all up. With test equipment, there's all kinds of different things. From one of my favorite tools is the classic VAT40 here, to power probes, logic probes, test lights, and of course, our multimeters there. That's what we're gonna focus on, but there's also oscilloscopes and all kinds of things. But you can do a lot of testing with some, knowledge up here, some smarts up here, a wiring diagram, and your meter, okay? And that's what we're gonna focus on in this class. Okay. Moving right along. I do have all kinds of, slides here on how to test for volts, how to test for ohms. But here's what we're going to do is I'm going to close this out. And what I am now going to do is share my screen so you see the whole screen. And with that whole screen, I'm then going to open up my document camera. All right, so let me do one more thing. Mouse up there. Okay. All right, and Tom, I got your question. I want to show everybody a few things on the with the meters here, and then we'll try to answer your question in a little bit of overtime. Okay. So I got the chat up. Can you guys just tell me? Can you see these two inexpensive multimeters up on my desktop here? What I'm doing while you're answering that, I'm going to take some of the wrappings up. Yep. Okay, good. You guys can see it. All right. So one of these I got off of Amazon, and the other one's the real cheap one from Harbor Freight. They work almost exactly the same, except that this one has an on-off switch down here at the bottom. This one, if I turn the selector, it turns it on. But you can see they got the same little transistor tester. They're the same function, the same basic design, and they're both less than $10. For testing stuff on your car, these things will probably work just fine. Where I don't really trust them is really more not just the meter, but the insulation of the leads. Even though if you zoom in on the lead, it says it can handle 1,000 volts. I don't really trust it. So I don't trust these meters if I'm going to be testing like a hybrid vehicle or doing electrical work on my house where I have 120 volts. I just don't test the insulation for that. But for your typical car, that's a 12-volt battery, they're going to work pretty good. Now, your most common measurement you're going to do is voltage. This meter does not auto range, meaning that I have to select the range that I want. I have to know what I want. So if I'm testing a car battery that is going to be, if it's dead, it's going to be at 0 volts. But if it's fully charged, it's going to be 12.6 volts. So 0 to 12 volts. Well, I have a range here that's 0 to 20 volts. That would be the range that I want to test at, okay? So I have to manually select the range that I want. It doesn't auto range for me. If I'm going to test ohms, well, here's that Greek omega symbol at the bottom. Again, I have to know, well, how many ohms do I expect to be testing? I have to manually select that. For most automotive circuits, it's going to be on the low end of the spectrum. It's going to be 200. Now, this meter, it doesn't tell me if I'm measuring volts or ohms, or I just kind of have to know what I have my selector on. I'll compare that to the snap-on meter. It has a nice display, and it tells you, hey, man, you're measuring volts. Or now you're measuring volts, and it's AC volts. Where with these ones, I have to know if I want to measure volts AC, I got to manually turn it to volts AC. All right. So one of the things I want to do is I want to test the resistance of each meter real fast and see if I have any variance between these three. So if I wanted to see how much resistance the meter had in its leads, I would go to ohms, and I'm going to take the two leads and touch them together, and it will tell me how many ohms of resistance are in those leads. It says 0.5, 0.4 ohms, maybe 0.6. It's mostly related to my connection. Now, I'll do the same thing with this one. Okay, so that one's a little bit less at 1.5. So if I was doing, now I'll do the snap-on one. I'll change them over here to ohms. And I'm going to test for ohms, and he says 0.4, 0.5, 0.6. So you can see the snap-on's got a little bit less resistance in it. Would that matter for most measurements? Well, this one had a few ohms, right? It had like 4 ohms in there. And now I'm down to 4 or 5. So if I was going to test a device, I would just have to, and actually as I sit here and hold it and wiggle these connectors and kind of rub them together, I get a better connection. And you notice that the resistance goes down. But let's say this thing always read 5 ohms. I always have to add 5 to whatever I was testing. So here, and this will come up in some of our activities for next week, I have a standard DIN, or what I'll call a Bosch relay. I'm going to measure his resistance across the control circuit, and it's saying 73 ohms. Well, if he had 5 ohms extra, I just have to remember that, oh, that added 5 ohms to it, and really it's not sitting at 73 ohms, it'd be sitting at 68 ohms. I could do that math if I was trying to compare it to a specification. I'll test this relay with the snap-on as well. You'll see that, yeah, you know, for the most part, it tested out the same. Is this a little nicer? Yeah, of course, this meter costs several $100s more, so I would expect it to be a little bit nicer, right? All right. So what about other things that you can test the resistance of? Well, I can test, in fact, I'll use this, well, I'll use both meters. I can test the resistance of my body here. If I take the meter and I hold its leads, I see nothing on the screen, right? But this is a manual ranging meter, which means that I have to select what range I want. Let me do that same test with the snap-on. The snap-on, by default, auto ranges, meaning that it can automatically select what range I want to test at. So I'm going to hold the leads in my hands, and it's thinking about it, and it says, okay, well, you have 0.8 million ohms of resistance in your body right now, 0.8 mega ohms. Okay, so, you know, what is that, 800,000 or so? So I have a lot of resistance, and that's why if I were to touch a battery or something, a 12-volt battery, I'm not going to really get shocked by that. But if I were to touch a, you know, a hybrid battery that has 300 volts, it could kill me, because it comes down to Ohm's law. How much voltage do I need to push current through my body? Why did this meter not read anything? Well, I have to manually start ranging him up. So I'm going to do that and see if I can get it to a high enough value. I don't think this thing will go. This thing only goes up to 20,000, and I was up at 800,000 or so. So, oh, no, there we go. So it can test my resistance, but I have to set the right range, right? So in some ways, these cheap meters can be a little bit harder to use, a little bit more sophisticated, because you as the operator have to know what range you want, right? If I'm, you know, testing a voltage that's very low, that would be different than testing a voltage that's higher. I want to say this 9-volt I have is almost dead. Let's see here. Now see how I hooked it up? I got this thing on the screen, and I hook up the leads here, and it just goes to this one. Let me start moving up the range. Oh, okay, so this 9-volt battery is pretty dead. It's only sitting at 0.36 volts, 0.35 volts, but that's more than 200 millivolts, and that exceeded the range. The other thing you'll notice is that when I hook up the leads backwards, does it damage anything? Not really. All it did was make that little negative sign come up. So that's what we call polarity, right? And you know, honestly, with digital meters, I don't worry too much about polarity. I know a lot of folks get tripped up on it, and I generally recommend students follow polarity so it doesn't mentally mess them up. But you know, I don't really care. I'm looking at what the number is, and I don't. This battery should be sitting at 9 volts, not 0.3 volts. So that battery is dead as a doornail. It needs to be replaced. But again, the meter didn't read anything when I didn't have it on the right range. So where this meter could, you know, you could get in trouble with this is, let's say you were living dangerously and you decided, hey, I'm going to test a hybrid battery with it that's sitting at 100 volts, which I would never really want you to do. But let's say you said, I'm going to test a hybrid battery that's sitting at 100 volts. If I had this thing set to this reading, it wouldn't come up with the reading because it's beyond the 20 volt range. I would have to move it to that range in order to properly see what that voltage was. All right, so a couple demos with those. Now, I like to end every class, and I know I'm over time. I like to end every class on a tech tip. Okay, so I'm going to give you a tech tip, and then if you guys want to continue to hang out, I'll go ahead and try my best to answer Thomas's question on his Honda. All right. So here's my tech tip for you. It's a very simple one, but I think it's hugely important. These stupid things right here. These are little alligator test clips, and my goodness, they will make your life so much easier when you start working on cars. These ones are the slip-on style, so this probe has no threads on it. I can just slip that guy on there, and now I have a nice alligator clip. And it just makes it so much nicer for testing circuits on my car or testing components, because oftentimes you'll get your readings will bounce around and you won't have good readings and you're getting frustrated. But when I can clip my leads on, I'll get a good reading that's consistent, and I don't have to mess around with it. So it will save you a lot of time. Now, some leads require a meter clip that screws on. So this one has a screw-on style of clip, right? And I want to say this other one is another one of the slip-ons. I got mismatched meter leads, but you kind of get the idea. The alligator clips that go with your meter make your life 10 times easier doing electrical measurements. So even though you might have bought this meter for $6 and it cost you $3 or half the price of the meter to buy those clips, they're still worth the $3 because they make testing circuits 10 times easier. One other little tool you're probably going to want to have, and it doesn't seem like it's very much of a tool, but it really comes up and makes your life a lot easier. It's just having some jumper wires. You can make these yourself out of stuff, or you can buy them. Having some jumper wires, again, makes circuits much easier to test. And next week, we'll get into testing relays and functioning those guys out, since we ran out of time tonight. So with that, I hope you guys enjoyed that information. I'm going to exit my document camera. All right, well, I know I burnt you out. I went way longer than I wanted to. I appreciate you guys hanging out. I hope you got something from it. Of course, I'll wrap up this video, this class, put it together a video for our classmates, but I really appreciate you folks being here in person, listening and following along. Always, if you have questions, you can send them to me on that tech help. I'll check that out and try to get those to you. Week 4 information is loaded up and ready to go as we kind of finish up week 3 here. So, all right, good luck. Hopefully you guys round up a meter, because you won't be able to have nearly as much fun in this class without having your own multimeter. Have a great week, everybody. We'll catch you next week, okay? Take care.